Okay, so we're in 4-2 now, Module 4, Section 2. We're talking about the end behavior of polynomials. So essentially that means what happens as I plug in larger and larger x's. So if I begin to plug in bigger and bigger x's, I guess here's a bigger and bigger x kind of color. So if I kind of plug in bigger and bigger x's, what's happening? So this means as x goes to infinity, because I'm plugging in infinity's way out here. So as I move to the right, this behavior, as I plug in bigger and bigger x's, this is called x going to infinity. Okay, which makes sense because x is going towards infinity. All right, and so we're plugging those in. We're looking at what happens to the y values. Okay, so let's kind of look at the y values now. So my y value is initially here, then here, then it looks like it's getting even lower and even lower. So it looks like the y values are getting lower and lower and lower. Okay, as x goes to infinity, what's happening to the y's? The y's are going in the y direction towards negative infinity. Okay, so as x is going to infinity, what we see is the y's are going towards negative infinity in the y direction, in other words, down forever. Okay, so so we're looking for that response here. As x goes to infinity, y is going to negative infinity. So that's this choice, and also this choice. Okay, so which one's correct? Well, let's look at the other issue. What happens when x goes to negative infinity? So going to negative infinity in the x direction means you just move to the left forever, because negative infinity is way out here. Okay, so this behavior is called x going to negative infinity. So we plug in these x's and we see what the y's look like. And it looks like these y's are also going down, 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 further and further. Okay, so as x goes to negative infinity, we see that y is also going to negative infinity. It's going down. Okay, which would be, as x goes to negative infinity, mean to the left forever. Y is going down forever. So this is true. And let's see, this is true. So the only answer choice where both the behavior at negative infinity and the behavior at infinity is correct would be this first choice in this case. Okay? Another way to think about this is just think about, as x goes to infinity, just think about yourself sort of walking to the right along the function forever. As I walk to the right, I go down forever. So that tells me this. Okay? As I walk to the left along the function, that gives me the other answer. That gives me the negative. As x goes to negative infinity, it gives me that information. As I walk to the left forever, I see that as I walk to the left forever, I see y's are going to negative infinity, going down forever. Okay? So you can also just think of it as walking along the function. But in reality, you're just plugging in either bigger and bigger x's or more and more negative x's. Okay? Now, the question about degree is interesting. Think about your good old buddy, the parabola, right? Isn't that your good old buddy, Mr. Parabola or Mrs. Parabola? Okay, so here is the parabola. And what's the equation for parabola? We all know our good old friend, x squared, right? Now, what's the degree of x squared? The degree is 2. The degree is the highest power. Notice both ends are going up. Both ends are going in the same direction. Is that the only way a parabola can appear? Well, it can also appear this way. What if I gave you y equals negative x squared? Looks like this, going points downwards. Okay, again, both ends are going in the same direction. Now, how about x cubed? Okay, x cubed looks like this. So x cubed goes up to the right, because 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, etc. This is y equals x cubed. How about in the negative direction? Negative 1 cubed is negative 1. Negative 2 cubed is negative 8. Negative 3 cubed is negative 27. So it's going down forever. Okay? So notice when you go to an odd degree is 3, we're getting the ends moving in opposite directions. Okay? What about if I put a negative symbol in the front? If I put a negative symbol in the front, that just flips this thing upside down vertically. So this would be the graph of y equals negative x cubed. Notice again the ends are moving in opposite directions from each other. Okay? How about x to the fourth? X to the fourth looks like x squared, just a little steeper. Okay, so x to the fourth looks kind of like this. It's actually a little flatter on the bottom and then a little steeper on the sides. So this is y equals x to the fourth. Again, same direction on each side. 1 to the fourth is 1. 2 to the fourth is what? 16, right? 3 to the fourth is, let's see, 3, 9, 27, 81, okay? Negative 1 to the fourth is still 1. Negative 2 to the fourth is 8. I'm sorry, 16. Negative 3 to the fourth is negative 3, negative 3, negative 3, negative 3 is 81, okay? Positive 81. So in other words, when you put something to an even power, the negative inputs still become positive, okay? Because when you go to an even power, you always get a positive answer, even if you plug in a negative number. What about if I put a negative symbol in front of, or a negative coefficient in front of the function? Y equals negative of x to the fourth. Then everything's going to flip vertically. It's going to look like this. Again, both ends go in the same direction. So what we notice here is, in the case where we have an even degree, both ends of the graph move in the same direction. Either both ends go up or both ends go down. Okay, and that's going to continue. What about if you have an odd degree, x to the third or x to the fifth or x to the seventh? The ends move in opposite directions. Okay, so because both of these ends are going downwards in this polynomial graph, I'm sure that I have an even degree. Okay, it's one of these scenarios. Now, the next question is, how do I know which end, like if both ends go up or do both ends go down? Well, it depends on the sign of the leading coefficient. If the sign of the leading coefficient is negative, you go down. Basically, the sign of the leading coefficient tells you what happens as you move to the right. So because I have a negative symbol here, I'm going to go down as I move to the right. If I have a positive, I'm going to go up to the right. Same thing here. If I have a positive 1, I'm going to go up to the right. If I have a negative 1, this is really negative 1, I'm going to go down to the right. The sign of the leading coefficient tells you what happens as you move to the right. How about what happens when you move to the left? Well, that depends on the degree. Is it odd or even? So if I know I go down to the right and I have an odd degree, that means I have to go up to the left because I have to go opposite. On the other hand, if I go up to the right because I have a positive leading coefficient, I'm going to have to go down to the left if I have an odd degree, because odd degree, opposite. Okay, odd degree, the ends move in opposite directions. Even degree, they go in the same direction. Okay, all right. So that's kind of just a quick synopsis of what's called the end behavior of the polynomial. Okay, end behavior means as you move way out towards plugging in bigger and bigger x's, either bigger positive numbers or bigger negative numbers. Okay, and when we say a bigger negative, technically that's a smaller number, but it's a larger overall sort of absolute value size. Like you're plugging in like -2, -4, -8, -10, -100, -1,000, that sort of thing. We're going towards more negative inputs or more positive inputs. That's called end behavior. All right, cool. So let's go on to the next example. Okay, so in this example, x and y intercepts, that's kind of a topic we've already talked about. Remember, we always make the other variable equal to 0. So if we want the y-intercept, we make x equal to 0. And when you make x equal to a certain quantity, life is easy, things are good, because you can just plug that in. Okay, so this one's real easy. You just make x equal to 0. Okay, so 0 cubed plus 0 squared minus 6 times 0 in this case is going to be just 0. So they want the answer as an ordered pair. So remember, the output or value of the function also represents the y. So when we say that the value of the function is 0, we're also saying the y is 0. Okay, because p of x is just a fancy function name for just the output y. Okay, so my y ends up being 0. So my input was 0 in this case, my output was 0. Now you might get a different answer on your version of the function of the problem. Now what about the x-intercepts? X-intercepts are hard because remember, you always make the other variable equal to 0. So for x-intercepts, we're going to make the y equal to 0, which means we're making the answer, this side, equal to 0. So we're going to end up with 0 equals the formula for the function, which means we have to solve an equation. Now, whoops, that's a square, sorry about that. Now, how do we solve this? Well, if it was quadratic, we could try factoring it. As long as it's set equal to 0, which luckily it is, we could try factoring. But it's not quadratic, it's third power. So let's hopefully be able to peel off an x. Is there an x that can be factored out of all three terms? And the answer is yes. Okay, so I have 0 equals, I can factor out an x, and I'm left with x squared plus x minus 6. We're factoring out an x from all the terms. Okay, now, will this factor further? Think of the x as its own factor. Will the x squared plus x minus 6 factor further? And the answer is, well, let's try it. X, I need to make a negative 6. So that's a 6 and a 1 or a 3 and a 2. What if I go plus 3 minus 2? Will that work? Would that FOIL out correctly? If I FOIL this, check it with FOIL. What happens with FOIL? I'm going to get first times first, outer times outer, inner times inner, last times last. Okay, and that adds up to this. Okay, so that is a correct factorization. Now, what does it mean that I have 3 factors multiplying to 0? What if I just told you, hey, I've got 3 boxes. Here's a box, here's a box, and here's a box. And if I multiply the quantities inside those boxes, I get a 0. Can you guys tell me what's in the boxes? I can guarantee you, 100% guarantee you, that the only way you can make this work is if one or more of those boxes is 0. Okay? So that means one or more of these guys has to be a 0. That's the only way to get a 0 with multiplication, is to use a 0. That's called the 0 property of multiplication. That's what allows us to solve for x-intercepts of polynomials, quadratics, and other types of polynomials. If we had any other number besides a 0 there, what if I had like a 10 there? What if I had a 10? Then I could do like a 10 times a 1 times a 1. I could do like a 5 times a 2 times a 1. I could do like a 20 times a half times a 1. I could do like a 10 times a half times a 2. I mean, there's a million ways if you had a 10. If you have like any number besides 0 on the right, there's so many ways that could occur. You don't know anything really. You have no knowledge of what these quantities could be. But if it's a 0 here, then all of this is invalid. That means you have to use a 0. That's why we always have to have a 0 on the other side when we're trying to solve for where a quadratic or a higher degree polynomial, has a solution. Okay? So that means either the x factor is 0 or the x plus 3. Each of these is one of your little mystery boxes, like in this little picture over here on the left. X minus 2 has to be 0. So this already has a solution. This is negative 3, right? And this is 2. Okay, so there's my 3 different x-intercepts. So that's just kind of a review of solving equations, polynomial equations that have higher power than a 2. You have to hopefully be able to factor out some x's, get it down to an x squared, and then use your knowledge of factoring the x squared to get the full factorization. Okay, and then you set each factor equal to 0, because if 3 quantities or more multiply and give you a 0, they each one independently can, if either any of them is a 0, it gives you a solution. Okay? Now, the next issue is, what about this, what's called end behavior? This is the end behavior question. Okay, what's a good end behavior color? I don't know, go orange, I guess. This is the end behavior. Okay, don't I have to graph it on my calculator? And the answer is no, I don't. Why? Do I know the degree? Boom, 3. Do you have to say boom? Nah, that's optional. Okay, maybe we'll cover that next week. All right, but anyway, the degree is 3, which is an odd number. So what does it mean that it's an odd number? That means the ends move in opposite directions. One goes up, one goes down. So it's either going to look like this. It's either going to go up and down like that, or like this. Up to the left, down to the right. Okay, one of those two. Which one is it? Depends on the sign of the leading coefficient, like we said before. In this case, the sign of the leading coefficient is positive. That's a positive 1. If the leading coefficient is positive, that tells you, the sign of the leading coefficient tells you what happens when you move to the right. That means I go up to the right. So if I'm going up to the right, I have to go down to the left. So this is my scenario. So that means as x goes to infinity, what's happening to the y? The y is going up to infinity. That's his infinity, sorry. So ugly, scary looking infinity. But anyway, it's going to infinity. Okay? What about if I go to the left forever? If I go to the left forever, x is going to negative infinity. What's happening to the y's? They're going down. Y's are going to negative infinity. Okay, so I don't even need to graph the polynomial to know what's happening and the ends. I can see that as x goes to negative infinity to the left, I'm going down. As x goes to the right, I'm going up. Okay? So as x goes to the right, I would be going to positive infinity. As x goes to the left, I'd be going to negative infinity. But that's because I had an odd degree polynomial, and I had a positive leading coefficient. Okay? All right, so let's go on to the next example. Okay, this is actually problem 6, an example of problem 6 on the assignment. In this case, again, intercept should be easy. You should be able to get these by now. Okay? If you're not getting those, that's, make sure to rewind the video and watch the previous components, okay? Or even watch the previous video, because I go over several examples of this. Just remember, always make the other variable equal to 0. And also remember that you want your answers as ordered pairs. Okay, it's x, y pairs. Right, the x and the y, that sort of thing. Okay? Now, what about the end behavior? Well, in this case, do I know the degree of the polynomial? I could try foiling this out, but that's a lot of work. I'd have to first FOIL x minus 3 times itself, because it's got a square on it, and then take that answer and FOIL that by the x minus 7. That's a lot of work. But I can already tell that if I did do that, if I did FOIL it out using a lot of FOIL, lots of FOIL, not just regular FOIL, but a lot of FOIL, lots of FOIL, multiple applications of FOIL, lots of FOIL, I would get something like this. I'm going to get, think of it this way, it's going to be x minus 3 times itself times x minus 7. So I didn't do the FOIL yet. Now I'm going to do the FOIL. Okay, I just wrote it out without the power. Now if I do the FOIL, I'm actually not going to do it, but I can tell you what the first term is. It's going to be the first times the first times the first. The first times the first times the first will give you the first term in the eventual FOILed out result. Okay, I'm going to have x cubed. Now if you want to know what the last term is going to be, it's going to be the last times the last times the last. And then you're going to have a whole bunch of middle terms. Okay, but I only care about the leading term. So I'm going to say x cubed plus lower power terms. Because I'm going to have things smaller than x cubed. This is all I need. Why? Because I already know my degree. What's my degree? Degree is 3, which is an odd number. And I also know my leading coefficient is, what was the coefficient? It's a 1 times a 1 times a 1. So the leading coefficient is a 1. 1 times 1 times 1 is 1. So I have a positive leading coefficient. So that's it. I'm done. I should be able to answer these questions. Okay? If you cannot answer those questions, you did not understand what we did before, and you should go back and review what we did before. Okay? Make sure you can do these. Make sure you understand what's going on. Okay? Now, if you want to get kind of a rough sketch of the graph, there's some interesting stuff going on here. This goes a little bit beyond the question, but it's stuff that we could use later. It turns out that since they're giving me the factored, this is called the factored form for the polynomial, which is really handy. If I would FOIL it out, I would get the FOILed form or expanded form. That's not as useful if you FOIL it out. Okay, the factored form is much more useful because in the factored form, anytime a factor equals 0, you get an x-intercept. You get if x minus 7 is 0, the whole height of the function at that x value would be 0, which means you're on the x-axis. When the height is 0, you're on the x-axis. So I already know, because of the factored form, this is going beyond the question right now, but that's okay, we want to learn. So if x minus 7 is 0, where does that occur? That occurs at x equals 7, right? That's an x-intercept for the function. You get an x-intercept whenever n of your factors is 0. So I know 7 is going to be an x-intercept. Okay, what else? What other x-intercepts? Well, I also have, if x minus 3 is 0, I guess we'll do this in a different color. If x minus 3 is 0, I also get an x-intercept. Where is that going to happen? At x equals 3, right? So that's another x-intercept. X equals 3 is another x-intercept. So let's mark that down. Now, you should have already deduced what's happening with your end behavior. If you did not do the end behavior yet, you should hit pause and try to figure out your end behavior, see if you get that right first. Okay? Did you hit pause? I can see through the screen. I don't think you hit pause. Go ahead and try it first. Right? Watching me do these is not going to help you. It's going to help you to sort of understand the process, but then you have to be able to do it on your own. Okay? Since this is odd degree, ends go opposite directions. Since it's a leading coefficient that's positive, I go up to the right. So I know my function is going to go up to the right. But since it's odd degree, it's going to go opposite directions, which means it's going to go down to the left. So what's happening at these x-intercepts? I know the function passes through these x-intercepts. What's interesting is that if the factor that gave you the x-intercept, what gave me the x-intercept of 7? The factor x minus 7. That factor of x minus 7 occurred one time. When a factor occurs one time, the function passes right through that x-intercept. It doesn't turn around, it passes through. There's two ways to have an x-intercept. Either the function passes through, or it kind of touches the axis and goes back in the same direction again. When you have a degree 1 factor, you get what's called a pass-through intercept. You pass through. When I have a degree 2 factor, what's happening with this degree 2 factor? I have two occurrences of the x minus 3, so that's a degree 2 factor. That factor gave me the x equals 3 x-intercept, right? The x equals 3 x-intercept came from the x minus 3 factor, but there's two of them. When you have an even degree, and the degree or number of occurrences of a factor is called the multiplicity. So I have an even multiplicity of this factor. And when I have an even multiplicity, the function actually acts like a parabola right around there. So it's going to come back up to go to that x-intercept, but it's going to kind of bounce off and act like a parabola right in this region. What do I mean by like a parabola? I mean, if I kind of magnified this right in here, it would look like a parabola. It would look like a downward parabola that has its vertex right at 3. Okay, and you can see that reason is when you get very close to 3, this factor is going to control the behavior of the function, and this factor looks like a parabola, like an x squared, that's been shifted 3 units to the right. This is a shift to the right by 3, right? So if you took x squared and moved it to the right by 3 units. Okay, now why is it pointing downwards? Well, that gets a little more complicated. It's because when you're near 3, this factor right here is negative. 3 take away 7 is negative 4. So that's acting like a negative coefficient and forcing the parabola to go downwards instead of upwards in that region. But the point is, when you have an even multiplicity, you're acting like a parabola, meaning you're hitting your vertex and bouncing off and going back in the same direction. Notice the behavior at the two x-intercepts lines up with the end behavior. We already knew the end behavior was going to be up to the right because we have a positive leading coefficient right here. And we knew it's going to therefore go down to the left because we have an odd degree, which means if you go up in one direction, you go down in the other. Okay, and then we piece together the fact that the 7 is a pass-through intercept because it has degree 1. The 3 is what's called a bounce-off intercept, or a quadratic intercept, in this case, because we have degree 2 there, or multiplicity 2 on it. And so then, therefore, I know it's going to kind of bounce off. And notice that behavior matches the end behavior. Now it joins up with the end behavior. Okay, so this is a rough sketch of what the function is going to look like. That we don't need that to answer the questions here, but we'll need that later on. So it's good to just address it now. All right, cool. So let's go on. Okay, so now we're on, this is basically problem 7 from the homework. Before we answer this, let's just think about our good old friend, the parabola again. So suppose I draw a parabola. I'm just going to draw an upward parabola. There's a few different ways to draw an upward parabola. Let me make this axis a little bit bigger here. I can draw them. I'm just going to draw 3 different parabolas for you here. I'll draw a blue guy. What should I call the blue guy? I'll call him blue guy. How about that? Okay, there's blue guy. Now I'm going to draw, I don't know, how about I'll draw one in red. What should I call that one? Yeah, I'll call that one that's in red, I'll call that green guy. No, how about red guy? That's a little better. We'll go with red. Okay, and then let's draw one in green. What should I call the green one? Let's call the green one, how about green guy? Okay, and there's its vertex. Now, there's 3 different versions of parabolas. In fact, I can kind of, we could kind of guesstimate an equation for them if we wanted to. Like this guy here, blue guy might be, could you guys guesstimate an equation? How about y equals, how about if I'm going, let's say this is at 3 right here, x equals 3. If I put some coordinates here, let's say this is at 3, and this is at, let's say, 2, and this is at -2. Okay, so what would be, could you guys give me an equation for the blue one? You should. Okay, I know it's going to be x I'm moving to the right by 3, which means I'm subtracting 3 from the x, because to the right, you have to force people to plug in bigger numbers, so you have to subtract 3 to force people to plug in bigger x's. Okay, and then I'm going to go up by 2. Okay? You don't need the equation, but it's good practice. Okay? How about the red guy? I'm still going to the right by 3, but I'm not adding anything. I'm not going up or down at all. So plus 0, which we don't have to write. How about the green guy? How about y equals x minus 3 squared minus 2, because I'm going down by 2. Okay? But irregardless of that, here's 3 different parabolas. And the question is, do they all have the same number of turning points, a point where it changes from going up to going down or from going down to going up? How many turning points does blue guy have? And the answer is blue guy has 1 turning point right there. Okay? How about red guy? 1 turning point. How about green guy? 1 turning point. Now, if you read through the chapter, they talk about the fact that you basically have at most 1 fewer turning points than you have your degree. What's the degree of all of these equations, all of these functions? They're all x squared. The degree is 2. Okay? So when the degree is 2, think about a parabola. So when you draw a parabola, the degree is 2. We all know what parabolas look like. How many turning points do we have? We have 1. 1 less. Okay? Next question is, what about x-intercepts? How about x-intercepts? They're talking about t-intercepts in the problem because their input variable is t, but it's the same idea. Let's think about it. We'll just call this an x-axis for now. Typically we use x for the input, but we could use other letters if we want. How many x-intercepts do we have? Well, it looks like I have either 0 x-intercepts. Blue guy doesn't meet the x-axis at all. Red guy has 1 x-intercept. Green guy has 2. Can you ever get more than 2? No, because if I slide down, let's go to purple guy. What's purple guy look like? Let's go to purple guy. Here's purple guy. Purple guy still just has 2 x-intercepts. No matter how far down you go, you're still only going to have at most 2 x-intercepts. Okay? So my x-intercepts are either 0 or 1 or 2. 0 for blue guy, 1 for red guy, 2 for either green guy or purple guy. Okay? So that means you can have up to as many intercepts as you have degree, whatever your degree is. So if degree is 2, you can have up to that many intercepts and 1 fewer turning points. And that makes sense because between the intercepts, there's probably going to be a turning point, right? So if you have multiple x-intercepts, you have 1 less turning point between them. Okay? So so now what about this problem? In this problem, I can rewrite the function in what's called descending order. What is descending order? Where the powers go down from the highest to the lowest. So if I write this in descending order, it would be g of t equals negative 3t to the 10th would come first, because that's the highest degree. Then plus t to the 8th, and then plus t to the 5th, and then plus t. Okay? Sorry that my t's look like my pluses, but you know. C'est la vie, as they say in, is that German? I think, oh wait, French. Okay. Anyway, so this is degree 10, right? Highest power. So the degree is 10. So if the degree is 10, think about how many intercepts you can have. Okay? And if you forget the rule, just draw yourself a parabola. Okay? If I draw a parabola, what's the most x-intercepts I can have? Degree is 2, most x-intercepts. Same as the degree. How many turning points? 1 less. So that tells you what to do here. Okay? Could you guys tell me the end behavior of this function? They're not asking it, but what if they did? You go up to the right or down to the right. You should be able to immediately answer that. If you did not immediately know the answer to that, it means even though you listened to the previous examples, you didn't follow them. You didn't really internalize them. What's the end behavior? Do you guys know the end behavior? Again, if you're listening to my question and you don't know the answer to what the end behavior is, you did not understand the previous examples and you need to go back and watch the video again. Okay? The end behavior is going to be down to the right because of a negative leading coefficient, and it's going to be down to the left because it's an even degree. Same direction on both sides. Okay? That would be my end behavior. They're not asking about end behavior, but what if they did? Okay? There's my end behavior. Okay? In the middle, it's going to be all wiggly because you've got degree 10, and so you're going to have a lot of wiggles. You have to have, with degree 10, you're going to have a lot of turning points. You're going to have a lot of x-intercepts. So it's going to be complicated, but I know the end behavior is easy. The end behavior is just based on the sign of the leading coefficient and the degree of the polynomial. Okay? All right, so let's go on. Actually, I think that's the last problem in 4.2. So I guess that's it for 4.2. Then we'll move to 4.3 in the next video. All right, that was fun, right? Wait, let me check it. Let me Google it. Yep, I just checked it on Google. Yep, that's fun.